Okay, last time we did simple probability. This time we're going to be doing probability of compound events. So basically you have two types of events. One where they overlap or where they don't overlap. And if they don't overlap, those are called disjoint or mutually exclusive. So basically those events, if they're disjoint or mutually exclusive, those events can't happen at the same time. Okay, so here's an example of a disjoint or mutually exclusive event. It says a card is randomly selected from a standard deck of 52 cards. What is the probability that it is a 10 or a face card? So if you use a Venn diagram, it really is helpful to see where these cards would, how these cards relate together. So if you're talking about if it's a 10, there are only 4 10s in a deck of cards. And face cards, there's 12 of them. So you can see that these two events are mutually exclusive. They don't overlap. Right here in the middle, right here, this is where they would be overlapping if they overlapped. That spot right there in the Venn diagram represents a card that would be a 10 and a face card at the same time. So there aren't any cards that are 10s and a face card at the same time. So that's why this is mutually exclusive or disjoint. So what's the probability of that? Well, the probability of that would be just add your two circle Venn diagrams. That 4 plus 12 is, so you'd have 4 out of 52 plus the 12 out of 52, and you'd end up with the 16 out of 52. And you can see that that also follows the formula over here where it's saying this formula right here that says the probability of A or B. So if these are mutually exclusive, it's just the probability of A plus the probability of B. And that's what happened over here. The probability of A was 4 out of 52, that was getting a 10. And the probability of B was 12 out of 52, that was getting a face card. Add them together, and you get 16 out of 52, which is what we have right here. When we add 4 and 16, or 4 and 12, we get 16. Okay, next one. This is an example of a compound event that is not mutually exclusive. So this one says, a card is randomly selected from a standard deck of 52 cards. What is the probability that it is a face card or a spade? Okay, so we've decided that in the deck of cards, there are 12 face cards, and there happen to be 13 spades. Remember, there's 13 of each suit in a deck of cards. Okay, but there are cards that are both a face card and a spade. Remember, this one right here, the overlapping area is where it's a spade and a face card. So if you want to figure out how many of cards that are both spades and face cards, there's 3 of them. So right here we're going to put a 3. But you have to be careful. If you put a 3 here in the middle of your Venn diagram, that means you have to take 3 out of your total of 12 right here. Because remember, this whole circle right here, when you're working with a Venn diagram, represents face cards, and those two numbers added together have to be 12. So 9 plus 3 is 12. So likewise, you have to do the same thing with your spades. If I'm going to put 3 in the middle, I got to take 3 out, so 10, because this whole circle right here represents the spades, and it has to add up to 13. So 3 plus 10 is 13. So that's what my Venn diagram looks like. So if we want to know what the probability of getting a face card or a spade, we can just add each of our circles together. So 9 plus 3 plus 10. So that's going to turn out to be, what is that going to be? 22 out of 52. So we've got 22 out of 52. So our probability is 22 out of 52. And we could reduce that fraction to 11 out of 26, divided by 2. So there's our probability. Now we could do the formula for this. So that was just looking at the Venn diagram, adding up our circles out of 52 because there's 52 cards in a deck. If we want to do the formula, the probability of A or B, so we have the formula right here for compound events that are not mutually mutually exclusive. This is our formula right here. Probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. The probability of A and B is where they're overlapping. So the probability of getting a face card, remember, was 12 out of 52. And the probability of getting a spade was 13 out of 52. And then remember, we had how many cards that overlapped that were the same? That was 3 out of 52. And if you add those together and subtract, you're going to end up with 22 out of 52, the same thing we got when we added our Venn diagram circles. So you could do the formula or you can do the Venn diagram. Both give you the correct answer. One is a more visual representation than the other. Okay, independent events. So independent events are things where the occurrence of one thing has no effect on the occurrence of another. For example, rolling a dice. If I roll a dice and then I pick it up and I roll it again, what I rolled the first time doesn't make any difference on what I roll the second time. Spinners. Spinners are independent events. If I flick a spinner and whatever color or number I land on, it doesn't really matter when I do it again. The previous spin has no effect on the next one. Replacement. So replacement is something like if you're taking marbles out of a bag and you want to know the probability of getting a red marble, and you pull a red marble out and then you put it back in the bag and you do the experiment again, that is considered an independent event. As long as you put back what you took out, that's replacement is considered independent events. So the probability of independent events, basically what you do is you just multiply those two probabilities together. So here's your formula right here, the probability of A and B. So if I want to have two events happen, it's the probability of A and B. It's the probability of A times the probability of B. So here's an example. For a fundraiser, a class sells 150 raffle tickets for a mall gift certificate and 200 raffle tickets for a booklet of movie passes. You buy 5 raffle tickets for each prize. What is the probability that you win both? So this right here, this is independent. Buying raffle tickets for the gift certificates has no bearing on the raffle tickets for the movie passes. So those are independent events. So the probability of you winning the gift cards, for the mall gift cards, you bought 5 out of 150. And then you bought 5 of the movie passes out of 200 of raffle tickets. Okay, so you could go ahead and reduce those fractions and multiply it out, and you'll get 1 out of 1,200. That's our reduced fraction. So that's the probability that you would win both prizes. Okay, now I have an example of a spinner. So this one says find the probability. Let's see, where'd we go? Find the probability of spinning the given colors. So if I spin a green and then I spin again and it doesn't matter, the probability of getting a blue doesn't matter whether or not I get a green. They're independent events. But I want to know the probability that I get a green, then a blue if I spin right after each other, 2 spins right after each other. So first of all, I guess we got to know how many colors total that we have over here. So if you count your pieces, it looks like, what have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we've got 12. And how many of those are green? So green, we have 1, 2, 3, 4. So we have 4 green. Blue, we have 1, 2, 3 blues. Reds, we have 2. And yellows, it looks like we have 3. So does that add up to 12? So it does. So there we go. Everything matches. Okay, so the probability then of spinning a green then a blue, the probability of getting a green would be 4 out of 12. And then a blue right after that would be 3 out of 12. So it would turn out to be 1/12. So if we were to do this experiment, what it's saying is that if I did this 12 times, I would get one of those combinations would be green then blue. So usually in class I go through and I do that experiment. So what I do is I just hit the spinner, and this counts as trial number 1. So it's a blue to start off with, so we wanted to have a green, so that trial number 1 is done. New one. So this is trial number 2, and I wanted to get a green, and I did get a green. So this is going to be spin number 2 on trial number 2, and it's a yellow. So trial number 2 didn't work, so now we're on trial 3, and that's a green. So we're going to do second spin of trial 3, red. So now we're on trial 4, yellow, nope. Trial 5, blue, nope. Trial 6, yellow. Trial 7, blue. Trial 8, red. Trial 9, green. So this is second trial of 9. Oh, yellow. So trial 10, green. Come on, blue. This is trial 10, second trial of 10. Oh, green again. Trial 11, yellow or red, and then trial 12 is yellow. So we didn't get it in 12 trials. Normally in class, when I do it throughout all the classes, I usually get one class where it works. Anyway, in theory, remember, theory and experimental don't always match, but in theory, if I were to do that 12 times, we should have got one of those combinations to be green then blue. Okay, now we'll just move on and do the others. We won't do the spinners. Blue then red. So if we're going to do blue, the probability of getting a blue is 3 out of 12. And the probability of getting a red is 2 out of 12. So if we multiply that out, reduce our fractions, we're going to get 1 out of 24. So 1 out of 24. So if I were to do 24 trials, one of those should be a blue then red combination. Okay, and then the last one is blue, green, and then red. So blue, once again, was 3 out of 12. Green is 4 out of 12. And red is 2 out of 12. So multiply that out, reduce your fraction, and you end up with 1/72. So 72 trials, if you did that experiment 72 times, one of them would turn out to be blue, green, and then red. That's what it's saying. That's the probability of that event happening. Okay, dependent events. So dependent events are things where one event has an effect on the other event. So for example, not replacing things when you draw them out of a bag or a deck of cards. Say for example, if I took out a jack out of the deck and I wanted to find the probability of getting another jack, but I didn't put the jack back in, that would affect the probability. Marbles, back to our bag of marbles. If I had a bag of marbles and I took a red one out and I didn't put it back in, that would affect the probability of pulling another red one out. So not replacing things is a very common dependent event. So our formula for that is over here on the right, the probability of A and B, given that it's dependent events, is the probability of A times the probability of B, given that A has already happened. That's what this notation means. B, given that A already happened. Okay, so whatever event A is, that it's already happened. Okay, so we'll do one. You guys are pretty familiar with this. We'll go ahead and do the bag of marbles. We'll do it both with replacement and without replacement. So it says a bag of marbles contains a bag contains 4 blue marbles, 3 red marbles, and 2 white marbles. What is the probability of selecting a blue marble and then a white marble? Okay, with replacement, you're going to put it back. So if I'm going to pull a blue marble out, there's 4 blue marbles out of, what's our total marbles in the bag? We've got 4, 3, 7, 2 is 9. So 4 out of 9. Okay, I put the marble back and I want to get a white marble, so that's 2 out of 9. As long as I put the marble back, um, I still have 9 marbles in the bag. So that's going to be 8 out of 81. Our probability is 8 out of 81. And then if I do without replacement, so if I pull a blue marble out, so it's 4 out of 9 getting a blue marble. Okay, I've taken one marble out of the bag. I don't know if it's blue or what the color is, but there's only 8 marbles in the bag now. So that would be 2 out of 8. And then that answer would turn out to reduce to be 1/9. That would be our probability of selecting a blue and then a white without replacement. So if I don't put the marble back. So dependent events were the effect of one. When you do one, it affects the probability of the second event. Okay, so now we're just going to do a few more with replacement, non-replacement with a deck of cards, just so you can kind of get the idea of how that works. So here we go. Find the probability of drawing the given cards from a standard deck of 52 cards. A is replacement, B is without. Okay, you want to draw a spade and then a club. So there are 13 spades, so that would be 13 out of 52, times there are 13 clubs out of 52. So if you put the card back, that's with replacement, there's still 52 cards in the deck. Multiply that out and reduce your fraction. So if we multiply it out and reduce our fraction, we get 1 over 16. Okay, now we're going to do without replacement. So if you are going to, the probability of getting a spade, there's still 13 spades out of 52 cards in the deck, but this time you don't put the card back. So I don't know if what the first card drawn was, and it doesn't really matter. The probability of giving a club is 13 out of, because the first one has to be a spade. So I guess the first one is a spade because we're doing a probability of a spade. So we draw a spade. And so now there's still 13 clubs in the deck, but there's only 51 cards in the deck because we don't put the spade back. So multiply that out, reduce your fraction, and you end up with 13 over 204. Okay, so on number 2, the probability of getting jack and then another jack. So there's 4 jacks out of the 52 cards. I pull a jack, and then I put it back. And so now there's still 4 jacks out of 52 cards. Multiply that out, reduce your fraction, or reduce your fraction first and then multiply it out. Either way, you get 1 over 169. Okay, now we're going to do without replacement. So there's 4 jacks in the deck. I pull a jack out and I don't put it back in. So now, not only do I have to reduce, there's only 3 jacks in the deck, but there's also only 51 cards in the deck. So multiply that out, reduce your fraction, and you get 1 out of 221. Okay, last thing is to draw a probability tree diagram. So this is a way of calculating probabilities also, compound probabilities. So this one right here says, using observations made of drivers arriving at a certain high school, a study reports that 69% of adults wear seatbelts while driving. A high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt, and 26% of the time when the adult does not wear a seatbelt. What is the probability that a high school student in this study wears a seatbelt? Okay, so when I read through that, that's pretty, I mean, there's lots of information there. It's pretty confusing. What we need to do is we kind of need to break down what's happening. And basically what's happening here is we've got adults who wear seatbelts or don't wear seatbelts, and we've got students who wear seatbelts or who don't wear seatbelts. So that's kind of what we want to do with our Venn diagram. We kind of want to, or not Venn diagram, tree diagram, sorry. We want to compare wearing the seatbelts and not wearing the seatbelts, adults versus students. So I think what I'll do is I'll start out with adults. So over here, this will be the beginning of my, I'm going to go left to right on my tree diagram. You could go up and down. Um, but basically what happens is one of two things. Either they wear the seatbelt, so this is yes seatbelt, or they don't wear the seatbelt, so no seatbelt. Okay, so if we go back and we read what it says a study reports that 69% of the adults wear seatbelts while driving. So this branch right here is our 69%. This is 69% right here. Okay, adults wear the seatbelt. So if they wear the seatbelt 69% of the time, then that must mean then down here at 31% of the time they don't wear a seatbelt. Okay, now depending upon what the adult does, that determines what the student's going to do. So now the student is going to do one of two things. The student is going to wear a seatbelt, or the student is not going to wear a seatbelt. And then down here, same thing. The student is going to decide whether they're wearing a seatbelt or no seatbelt. So what we've got to do is we've got to figure out what the percentage there is when, so when the adults wear a seatbelt, so let's go back and read our sentence. A high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt. So this right here then would be 66%. Well, then that must mean then that 34% are not wearing their seatbelts. And then 26, it says, let's see, what else we've got going on here. So let's see, when the adult wears a seatbelt. And 26% of the time when the adult does not wear a seatbelt. So down here, the student will still wear a seatbelt even if their parents aren't wearing a seatbelt 26% of the time. So then that would mean that 74% of the time they're not wearing a seatbelt. Okay, so to answer our final question, it says, what's the probability that a high school student in the study wears a seatbelt? Well, what we're going to do is these are two compound events. We're going to follow the path where they wear the seatbelt. So right here is where they wear the seatbelt. So it's this one right here combined with this one. So that's going to be 0.69 times 0.66, and that's going to turn out to be 0.4554. And then we'll do the other one when the student is wearing a seatbelt. So that's this branch right here, and it combines over here with this one right here. So these two are, that's the branch we're following. So that would be 0.31 times 0.26, and that turns out to be 0.0806. So those two probabilities, we would want to add those two together because it's two different scenarios. So we'll add those two together, and we end up with 0.536 as our probability that they're wearing a seatbelt. Not very good. I hope this is not accurate data. We would want you to be wearing your seatbelt 100% of the time, regardless of what your parents are doing. Seatbelts save lives. All right, next problem. You are off to soccer and love being the goalkeeper, but that depends on who the coach is. So with Coach Sam, the probability of being the goalkeeper is 50%, 0.5. With Coach Alex, the probability of being the goalkeeper is 0.3, 30%. Sam is coached more often, about 6 out of every 10 games. What is the probability you will be a goalkeeper today? Okay, so same thing. I am just going to start with a tree diagram. So we want to figure out the probability of being a goalkeeper today. Well, it kind of depends on who's coaching. So we start out with a coach, and it's either Sam or Alex. Now, when Sam coaches, you get to be goalkeeper 6 out of 10 games. So that's 60%. So that would mean then when Alex coaches, you're only goalkeeper 40% of the time. Okay, and then let's see, what else does it say? The probability of being a goalkeeper with Sam is 50%. So right here now, so we'll follow along the branch of Sam coaching. So if Sam is coaching, you can be a, I kind of made my diagram there a little bit too high. We can be, so it's going to go a goalkeeper or no goalkeeper, right? So it's 50-50 when it's with Coach Sam, so 0.5. Okay, now Alex, not so much. Alex doesn't really like you. Coach Alex doesn't really like you as the goalkeeper. So goalkeeper when it's Alex is 30%. So no goalkeeping would be 70%. So remember, we want to know what's the probability we get to be the goalkeeper today. So let's follow those branches of where you get to be the goalkeeper. So that's this one right here and this branch right here. So if you go ahead and multiply those out, it's 0.6 times 0.5, and that's going to be 0.3. And then the other branch is 0.4 times 0.3, so that's going to be 0.12. So we're going to add those two probabilities together. So the probability that you get to be goalkeeper today is 0.3 plus 0.12, so that's 0.42 or 42%. So just a little bit under half, 50-50. Not quite 50-50 if you get to be the goalkeeper. Okay, so that's compound, different types of compound probability. So you've got to remember, is your event independent or dependent? Are they, do your events overlap? Do they not overlap? All those kind of things are going to help you try to figure out what your probability is going to be.